Hello, let's understand what is KL divergence. So we look into the definition, the intuition, some behind the scene concepts like entropy, cross entropy, something from information theory, and we'll build an insight and also look into some properties of this KL divergence. So KL divergence is given by this formula of between two different distributions P and Q is given by the expectation under the distribution P log of P by Q. Now let's understand what do we mean by this. Let's get into some definition. KL divergence is the measure of the difference between two distributions that are probability distributions, or we can also say how much one distribution is away from the true or the reference distribution. So sometimes in optimization techniques, we assume one distribution and we try to get it closer and closer to the true or the reference distribution. Assume this being the true one and this being the assumed one. So how do we measure that difference is given by, or we quantify, or we map a numeric value to that difference, and that is given by the KL divergence between the two distributions P and Q. It is also known as how much information is gained when we try to assume one distribution as Q instead of using the actual distribution or the two distribution or the reference distribution P. Now, how is that? How does that happen? When does that happen? Are the things that we're going to look into. Let's first check what entropy is. Entropy is nothing but a measure of randomness, a measure of unpredictability, a measure of uncertainty, also sometimes known as a measure of surprise. While sampling from a distribution, or how much surprised are we when some event happens. So when we sample from a distribution, we get something, how much surprised are we? We also sometimes say the less likely the event is, more surprise we get, or highly likely event, less surprise we are. We can look into one example as in, let's assume there is a chef here and we are there in some restaurant food and food. We go to the chef and we say, surprise me. Now the chef goes into the kitchen, gets something cooked, brings back that thing to you, and then you are surprised because you never knew what is the dish that a chef is going to bring for you. Now you said, oh, I'm not actually liking this. Can you bring something else for me? Now the chef goes back, again cooks something you don't know, bring back that dish for you, and you're surprised again. So there is a sense of randomness in what the cook is going to bring to you. Assume that the cook is always going to get you a pizza, you would be lesser surprised because now that is a bit deterministic behavior from the chef that is happening. That is some predictability that is there. You already know that there is no sense of randomness. So the more you know about something, the less surprised you would be, or the less random behavior that it would be. Now, I assume you never expected this thing to be played in the middle of this discussion. This was very less likely, so you are more surprised, I assume. We can take another example as to build some intuition as to why we are saying that surprise is equivalent to some information. Assume that instead of sun being there every morning, the sun and the moon decide that either sun will be up at 6 o'clock or the moon will be up at 6 o'clock. Now every time you don't know, there is a sense of randomness because you never know whether it will be light or whether it will be dark again or have some light because of the moon. Look, based on the occurrence of these events, as in whether the sun is going to be out or the moon is going to be out, instead of you already know that sun is anyways going to be out every morning, if there is some sense of unpredictability there, now your that would cause some information to be there, because based on that information, the rest of your actions are going to be decided. So you need some information, as in if you're in a room, you ask your friend whether the sun is out or the moon is out, because that is the information you need to decide rest of your tasks. Nowadays, if you do send a text to your friend, as in, hey, the sun is out there at 6 o'clock, it's very less informative. That friend already knows that the sun is going to be out there in the morning anyways. So that is some sense of deterministic behavior that is happening, and that is going to give you less information, and that is going to give you less surprise. Now, how do we quantify this information? We say that information is given by negative log of the probability or the likelihood of that event that is going to happen. And we can see from this plot, this is the negative log graph. You can see that lesser the probability or the likelihood of an event, the more information it is having. And if I increase the deterministic behavior, the lesser information it is going to be there. This is a simple probability distribution for a discrete variable, and this is a simple probability distribution for a continuous variable. But the same would be applied here. So this P of X could be either for a discrete random variable, or for a continuous random variable. Let's build some more intuition. Okay, so how do we guess things? We guess things if someone asks you, okay, guess what happened? You try to answer in terms of what could be the most probable event that would have happened, and you first tell that as an answer. You try to reduce your answer space, if you can say, in terms of giving the most obvious or probable answers first, because you know that are the most obvious ones that might happen. And then, because you know there could be some sense of deterministic behavior there, and that's why you just, and why do you do so? Because you don't want to waste more time in telling what was the most unlikely event that happened, because you already know that this is the most unlikely thing that is going to happen, and the answer from your friend would be no, not this is not the case. Then you will be asking again a very less likely event that has happened, and your friend would again say no. So you want to optimize, you want to guess the thing in less number of questions, you want to have an optimal behavior, and that's why you start with the most probable ones. Let's get some example. Okay, let's assume that there are 4 balls, blue, red, orange, and green, and in in a room. And first case would be all the balls are blue. So this is how the probability distribution would look like. All the balls, the red, orange, and green are 0, and we have all blues. Now, if someone gives you this distribution, and behind a curtain, they just pick one ball from it, and then they are asking you, hey, can you guess what is the ball that I've taken out? And you already are having this distribution as your cheat sheet. It is, you won't be surprised. They would ask you, do you need any hints? You would say, no, I need 0 hints, because I already know that whatever that you have taken out from the bag is a blue one. So how many number of questions do you need to ask to predict whether the ball that was taken out from the bag is a blue one or not? It's very simple. See, the probability for a ball to be blue is 1, and log of 1 is 0. You need zero questions. You need you need zero information, and you won't be surprised. How much information you would get if blue is the ball that is being taken out. Let's assume that they take out red ball. Now, wouldn't you be surprised? Because log of 0, you would be surprised max. As in, how is it possible? Because from my probability distribution that I have, the probability of red being there in the bag is 0. It shouldn't be there. And you would be surprised max. Let's take another example. So this is a more deterministic behavior that is happening. You don't need any information to guess this. Now, let's assume there are equal number of balls. So the probability is 1 by 4, 1 by 4, 1 by 4, that is 0.5. Now if your friend asks, hey, what do you think? I'm taking a ball from this. What do you think is the color of the ball? Now you don't know anything about it because every ball is equally likely. So what could be the most optimal one? What could be the most worst behavior from yours? You will simply ask, is it green? Is it orange? Is it red? Is it blue? And worst case scenario would be you are going to ask 4 questions. You are going to have, if we just quantify information as in number of questions, it is 4. But an optimal behavior would be you can simply guess in just 2 questions. As in how? First you will ask whether is it something from red or blue. If the answer is no, then you know that it is either orange or green. And then you would simply ask, is it orange or is it green? If the answer is no, then you know that it is green. And if the answer is yes, then you know that it is orange. Same thing applies in here. If it is yes. So the most number of questions that you're going to ask is just 2. And how can you quantify this? How can you have a numeric value for this? Because you are having log 1 by 4, that negative log of 1 by 4, and that is given by 2. So this information actually gives you how many number of questions or how many number of hints do you need to guess what that event would be. How many number of questions do you need to guess whether it is blue? How many number of questions do you need to guess whether it is red, orange, or green? And because in this case, every event is equally likely possible, then we need equal number of questions, as in 2 in this case. We are taking log of to the base 2, but so when we take log to the base 2, that information is generally known as bits. If we take natural log, as in log or ln, that is generally known as nats. Let's take another case in which all the probabilities are different. Green is the most highly likely possible. So, and if your friend simply asks you, and you already are given with this cheat sheet, this probability distribution, and this aligns with the one, how are they distributed in the bag? So they are distributed in the bag according to P, and you are also given P. See, this is being sampled according to P, and this is the cheat sheet. Now you already know that, okay, I think so green could be the most probable one. So you first guess, oh, is it green? Either they will say yes or they will say no. So it means that you are going to guess that in just one question, one question, or just one. So to guess whether it is green or not, you need less number of questions or less information to guess whether it is green or not. Because once the green is gone, now you can see that Now you have more random behavior because these values are more closer to each other. Now more, they are almost equally likely possible. So now, I mean, this is a bit more probable, and similarly, you would need those many number of questions. So how many number of questions you are going to ask? As in, I'm just taking the negative outside. These are these are many number of questions you are going to ask for green. If you want to guess if it is green or not. If you want to guess whether it is blue or not, then you're going to ask negative of log of 0.2 or negative of log of 0.15 or negative of log of 0.15. So these are the questions that you are going to ask for each and every ball to predict their possibility of taking out from the bag. Now, what do we mean by entropy? Entropy is nothing but the average or the expected surprise or information. So all these things that we discussed, we can also say that I'm quantifying surprise with this. I'm quantifying how much information. If I want to give a numeric value to surprise, I can say that like negative of log 1 or negative of the probability. So on an average, for all the events that are going to happen, on an average, what is the expected surprise or information? So how do we define information? Information is given by this, and how do we define expectation? How do we define expectation of something? Is given by expectation of information of a random variable, that is x, being sampled from a probability distribution. This is given by a summation of the probability of that event to occur and this information. And this is given by nothing but this formula. This is for discrete random variables, and the same thing could be applied for continuous random variables, as in this is information, this is the negative sign, I have taken the negative sign out, and this is known as h of p. The entropy is defined as h of p. This p is how the distribution is and how much average information are we getting for all the possible events that are going to happen for this distribution. We can also sometimes write like this, h p of p, as in this was the probability distribution from which we were sampling the events, and this is the probability distribution from which we were getting the information. This was our cheat sheet that we already have, and this is the one according to which we were sampling our values. And this is nothing but entropy. Entropy is average or expected total information that we are having. Why total? Because as we saw in here, in this case, how many number of questions are we going to ask? 0 in this case. How many number of questions are we going to ask? 2 in this case for every event. For blue also we are going to ask 2 questions. For red also we are going to ask 2 questions. For green also we are going to ask 2 questions. And for orange also we are going to ask 2 questions. So total number of questions for blue are 2. Total number of questions for red 2. So that is why I'm saying the total number of information, but on an average, because we are taking an average for all the possible events. So we saw that in a case where every color was blue, it was more deterministic, right? We were never surprised if it was blue. We were having very less information. We actually need 0 information for that, 0 questions for that. So that is why if our probability distribution is a skewed one, is a very, so like these are the only events that are highly likely. These events are very less likely, right? So it is a more skewed distribution. It is more deterministic. Less random things are going to happen. Likely outcomes are there. You already can predict the outcomes easily. Less surprise you would be, less information, and therefore less entropy. As simple as that. Similarly, if we have a relatively balanced or uniform distribution, like we had in case 2. These were This is a very balanced distribution, equal, right? All the events are equally likely possible. So if the distribution is balanced or uniform, we have less deterministic behavior, more randomness is there, less likely. The outcomes are very less likely. The more surprise, the average number of surprise would be more because all the probability is less, right? But still, if it is if it happens, then oh, I didn't assume that. I never assumed that thing. I never predicted that thing to happen. And that's why you would be more surprised because that those events were less likely. The more information you would gain, like the sun and the moon example, because the rats and there was a sense of randomness. And that would lead to high entropy. So we look into cross entropy the next time. And that is it for what do we mean by entropy. And we look into cross entropy, and then further we look into how we can relate these terms, the entropy, cross entropy, all coming together as KL divergence. Thank you.